Last video, I said I'd cover the nozzle. Turns out the nozzle runs on the same exact principle that makes an airplane wing work, known as the Bernoulli's principle, but it's just used completely differently. And once you get that, the fuel problem is where things actually start getting complicated. This is my nozzle. Notice the shape. It narrows down to a point, then widens back out. That's called a converging-diverging nozzle, and sometimes also known as a de-Laval nozzle, and it's the actual shape used on real rocket engines. Here's why the shape matters. If you got a fixed amount of exhaust moving through this thing every second, when the passage narrows, the same amount of gas has to squeeze through a smaller space, so it has to speed up because there's nowhere else for it to go. And that's actually where Bernoulli's principle comes in. Bernoulli's principle says as a fluid speeds up, its pressure drops. Imagine us running, right? As we run, we feel a short burst of air hitting our face and pushing against our face. And that's relatively small pressure. But if we crash into a wall, ouch, it would hurt because the wall pushed back on our face, a huge amount of pressure. And also, as we hit the wall, we lose all of our speed. So what do we learn from this example? A moving fluid has energy tied up in mainly two places, its speed and its pressure. That total energy can't just appear or disappear, just like how we know Einstein says energy cannot be created or destroyed. So in our case, it can only shift between the two. So if this fluid speeds up, more of that energy is now in motion, which means less is left for pressure. And naturally, this would work vice versa. As pressure goes up, speed has to come down to balance it out. Let's visualize this in effect, but instead of using air, let's use water as an example. With water, it is called the Venturi effect. Same amount of fluid, but just as water. But now it's moving through a pipe. At the beginning, our speed is small, so our pressure is high. But as we go down the pipe, the water begins hitting the sides of the pipe and narrowing into smaller space, increasing our speed and lowering our pressure. And then getting released into a big area again where we ease back into high pressure and low speed. That's the energy shifting easily made visible. That's exactly what happens inside my nozzle. The gas gets squeezed through a narrower space at the throat, so it speeds up, and the pressure drops there as well. It's the same rule with the water, but just with rocket exhaust instead of water this time. Then past that point, the nozzle widens back out, and the exhaust keeps expanding and accelerating out the back. All that high-speed gas shooting out the back is what generates thrust. And with Newton's third law, every action has an equal and opposite reaction. So the gas that's getting pushed backward or under us, the rocket gets pushed forward or upwards. Now here's where it actually gets genuinely wild, because you'd think that if you just want a rocket to go faster, you just give it more fuel. But it's really not that simple, because fuel has weight, and that rocket has to carry that weight as well. This is called the Tsiolkovsky rocket equation, named after the guy who figured it out. It's the actual formula every rocket engineer uses to calculate how much fuel you need. That's why rockets are mostly fuel by weight, not payload. The actual thing you're trying to launch, the satellite, the crew, the capsule, whatever it is only a small fraction of the total mass. Most of a rocket is just fuel trying to carry fuel trying to carry fuel. This is why every gram of a rocket matters. It's why the nose tip shape, the nozzle shape, the wing sweep, all of it gets obsessed over meticulously. Every bit of drag or inefficiency means carrying even more fuel just to compensate, and that fuel isn't free. It's not weightless. It costs mass and money and even more fuel. So that's the nozzle and the fuel problem. Bernoulli's principle explains how the thrust actually gets generated, and the rocket equation explains why every ounce of efficiency in the design matters so much. All my CAD files, sims, and writeups are linked in the comments below if you want to actually see the work. If any of this made sense, or if you got any questions, drop them below. This is everything I did at session 1 in Northwestern, and see you in part 4.